So we all know the standard story that we come to the end of automatically scaling because of technology. And the FPGA companies have had a wonderful ride over the last 20 years. Every year the question was, shall we do something new in architecture? And then the silicon guy said, well, I can get you 2x in the process. 2x in the architecture is hard. That's a lot of work. So for quite a while, the silicon guy said, let's just do the next node and same architecture is good. However, that's coming to an end. So now you need to do something that is actually architecture specific, but the next step, and I'll show you, the question is for what application? And so you need application knowledge that is potentially domain specific, like 5G, wireless communication, video, machine learning, to figure out what would be a good solution. The second piece that we have focused on enormously is classically FPGAs were not that hard. Classically, FPGAs did a very similar thing as conventional ASIC. Logic synthesis and place and route, and that works well. But if you continue to keep on scaling that, you'll run into a particular long running times for that classical style. We're talking logic synthesis of hours, we're talking place and route of hours, and the competition shifted. It is not anymore, can I build an FPGA classical style, but can I entice the software developer to use my platform? And so we have built with ACAP actually two customers-facing solutions. One, the traditional hardware developer should get everything we build in 7 nanometer very usable, and the conventional software developer who thinks in C, C++, and we've done also a whole bunch of Python-style interfaces, should just be able to use it without needing to know all the super low-level details of the various platforms. And so it's all about abstracting the hardware and providing software frameworks that make that usable. We've essentially built a new platform with new target audience. So we're trying to reach data scientists, software developers, and we have built, and I'll walk you through a little bit of the particular platform in more detail, but we've built essentially a combination of technology and a particular innovative new technology, and I'll talk about that. But it is basically also geared towards deployment in a range of applications, all the way from large, think data center, to really small, think IoT, automotive, and embedded. And for those who are familiar with Xilinx technology, historically it was, we have a catalog of parts, you figure out your problem, and then after you've done your homework, you figure out which part in the catalog works. This is slightly different. This is towards the things that you can do, partly driven by power constraints. We can build things that are 100 watt, we can build things that are 10 watt, and we can build things that are a few watt. So what is it? So I'm on purpose throwing the whole thing in one slide and not a build slide, and I'll walk you through it step by step. Since our Zinc products and our Zinc MPSoC, we have always rolled products with ARM processor into it, and that has been highly successful. So we are building all our new parts always with processors in there, if and only to really run it, boot it, do control software, and so on. We have basically a conventional ARM large cores and real-time for sort of interrupt handling and small, and this is in ARM terminology, big little particular choice. We have further hardened the things that you always need. So just like you would do in conventional SoCs, we have PCI Express, and in this particular case, this talk won't address that much further, our cache coherency protocol CCIX on top of that. We have DDR hardened interfaces. There's a line coming out with HBM interfaces. We have a traditional strength of Xilinx high-speed serial I/O. We have traditional strength of Xilinx Ethernet Max, and we have, if needed, model parts coming out with RF interfaces, read A to D and D to A conversions in the high gigahertz ranges. Additional, also new for Xilinx, is a network on chip. If you know that you need to communicate to your external memory, you can use FPGA style wires for it, but if that's all you need them for, you're better off putting in a dedicated network. That's a new technology. And then I'll zoom in a second on what these AI engines are. The adaptable engines plus DSP engines you should think of as the classical FPGAs that already have embedded lookup tables for bit-oriented operations, multiply accumulators for multiply accumulate functions, and embedded memories, Xilinx terminology, block RAMs and ultra RAMs. So let's zoom in to the new part, these adaptable intelligent engines. As I said, it is very important, if you build something new, to understand what the application domain is. And so we've chosen this application domain to be in the top two are shown up there is basically 5G, autonomous driving and signal processing, and machine learning is the one that is emerging rapidly as an essential part of it. What we've also seen is you can do this in the traditional sense, right? You can build a traditional DSP, one or more, and then you'll get a certain level of performance. The key added value is that we've built a very large multi-core environment for this and the programming environment for it, and I'll talk a little bit more about that. What you also see is that one of the reasons why this is getting relevant is the new applications have enormous compute requirements. That is true for 5G infrastructure, that is true for machine learning, that is true for machine learning in the data center, that's true for the machine learning in the IoT devices, that's true for the machine learning in automotive devices. And so you see that there's an enormous opportunity for silicon companies that can offer the right performance for the right amount of power consumption to have new devices. Now, we talked a little bit about this just before the break. Traditionally, you would compete against custom ASIC, and you would, let me see if I can get the cursor to work. Traditionally, you would compete FPGA against an ASIC. But the real question, so you might get in your ASIC your device and power efficiency and maybe the throughput and latency and maybe a cost reduction, but you don't get the flexibility and the programmability and the software programmability. Now you can go to the other end of the spectrum, and you can use your CPU and GPU that are perfectly fine software programmable, but they miss the fact that if it isn't in there, it gets really inefficient, which is why you see in these SoCs emerging a whole bunch of hard ASIC blocks that is sort of the kitchen sink of all the things they can think of that potentially can do it. So our philosophy here was stay at the programmable end, combine software programmable processor cores and FPGA fabric the right way, and we'll talk about that in a second. And what you see is, compared to conventional FPGA fabric, this looks much more like an SoC plus something. And it's closing the gap historically where FPGA customers said, well, if the volume goes up, I need to build my own ASIC. Well, if the volume goes up and you would integrate these processors like we have in our current part, then we have that part for you. That distance has been diminished. So we're going to build something that is gigahertz range and up, programmable cores. To give you a feel for it, our largest device that is the first device that will be available, will have 400 of these. And so this is very different than your run-of-the-mill 4 or 5 or 10 DSPs. And we'll talk about that. It is good for signal processing, it is good for computer vision, it is good for artificial intelligence. I'm not going to go in enormous amount of detail, but it is built to have a software flow. So from the beginning, I think of the algorithms that I want to do. I will show you in more detail the compile steps that will buy you that, and then the run steps. This is not your conventional logic synthesis, place and route anymore. And typical times that we see are minutes to tens of minutes for this multiple compile step. There's also two things that are important here. For the machine learning, we will offer a complete framework interface where you start at, say, Caffe Prototext or ONNX or TensorFlow graph, and we will do the whole compile flow for you. For the applications like signal processing, amongst others, 5G wireless, machine vision, image processing, we offer you a C++ abstraction of the graph that then runs kernels on the individual processors, and we'll go in more detail on that. What you see from an application domain is that uniquely, because we have FPGA fabric in classical sense and ARM processors next door, we don't have to do everything with our adaptable intelligent engines. So it allows us to build a highly tuned engine that not necessarily solves all your problems. Sometimes, and we'll talk about that in a little bit more detail, sometimes in processor design, the biggest problem is what don't I stick in? Because then it gets bigger and bigger, and it gets more and more silicon, and gets more and more power, and it's less optimal than you think it is. So our existing FPGA fabric has already lots of flexible embedded memory. And you can build with these devices embedded memory hierarchies depending on the application. After you know your application, you can actually design the memory hierarchy the right way. What you get for this is, because it is all on chip, the communication bandwidth already inside the FPGA, and everybody knows that, is terabytes, but also the communication bandwidth between our FPGA fabric here in red and the AI engines here in green is also terabytes. So you can literally get out of your processor, do a little bit in the FPGA fabric, and get back into your processor without burning enormous amount of power, without hogging enormous amount of data connections. See here is, we compare this to our existing Xilinx UltraScale, so that is the previous generation from a 7 nanometer point of view. That is the current generation in the market from silicon available today. And we have done a whole bunch of applications all the way programmed out, and we see 20x to 5x for the applications where it is really used for, and at least a 2x power reduction. And as an application engineer, you can slice this in different directions. If you stay with the same compute as you previously had, you of course get more power benefit. Let's zoom in on what these are. So these are instruction set architecture-based vector processor, and these are conventional programmable, like many of these processors are, with, for some simple application, vectorization works. For a large number of applications, you write C and C++ vector-style code with function intrinsics. This is industry standard. This is essentially also how you do this for your AVX processors in the CPU world and all the other DSPs from the current vendors in the world. That makes sense. We have special 5G wireless instructions. Think of it as digital pre-distort and so on, highly tuned. Think of it also as FFT, highly tuned, that works very well. We have local memory, and that is multiple banks, and we'll show you why in a second. That is for two reasons. One, the local processor has multiple load and store units, and second, the communication between the processors depends on these banks, and therefore we have a choice of number of memory banks. We have chosen to do not cache coherency and to see if we can build deterministic interconnect, and we'll show what that buys you in a second. We have chosen to build hardware, DMA, and semaphores so that the compute can keep on running while the communication between the processor is running. We have chosen also, think of it almost FPGA style, to do a cascade interface, which is, think of it as if we build these vector processors and I do a multiply accumulate, the number of bits in your accumulator is significantly more than your conventional vector path. And in conventional adder trees, you sometimes have the accumulator tree connected to each other that is more bits than the standard data type. That's this cascade. And now we'll talk about how you can get deterministic performance and deterministic latency out of this. So we have, this is close to FPGA thinking, a tiling of processor architectures, and each processor can see the memory of its neighbors, but nothing more. And I'll come to it in a second on how this really works. And we have, this is all public domain data. You can go to the Xilinx website and you can see that we built devices with 400 of these cores, over 100 teraops compute in those devices. And you can see the details in the data sheets. It is a distributed memory hierarchy, and the tuning is towards the right size and the right amount of memory bandwidth. If you zoom into it, this is a scalar processor and a vector processor. It is a processor with 2 load units and a store unit. These AGUs are these address generator units so that I can do auto-increment on buffer pointers, and a conventional instruction fetch and decode unit with a flexible format in bit interface. Interesting interfaces to both a load store interface and a stream style interface. 512-bit SIMD data path. What that buys you is that you can do over 7, depends a little bit, everybody starts arguing on how to count VLIW or FLIX or anything else. What it buys you is essentially the most important part is for typical workloads, I can do a vector SIMD operation every clock cycle. And concurrently, VLIW processor style, the loads and stores can be scheduled, the scalar operation can be scheduled, the auto-incremental, the buffers can be scheduled, and the DSP terminology zero overhead loop can be executed. So this is really a processor that once you start writing C programs and C++ programs for it the right way, can sustain, get very close to the peak performance, and I'll show you a little bit of the data in a second. We have also chosen to support multiple bit types. We have 8-bit, 16-bit, 32-bit. We have complex values and single precision floating point values. What that gets you in this particular case is in a clock cycle, I can do 8 single precision floating point or 8 32 by 32-bit reals or 16 32 by 16-bit reals, and you can see it all the way up to, in particular, for the 8 by 8 reels in convolutions, we've done something special. We can do 128 of these reels that are the workhorse of 8-bit machine learning convolution engines. You see also that in the wireless communication domain, you have quite often 16-bit I and Q values, and you want to do complex arithmetic, and you can do here 8 16 by 16-bit or 16 of these multiply accumulates per cycle. Let's take a look at how the communication model works. So these processors run essentially buffer to small buffer, and the whole concept is to keep the buffer to buffer streaming. And so if it is the same processor, it just writes to its memory, and the next function call reads from the same memory. If it is the neighboring processor, then it writes to a buffer, and we do a standard double buffer ping pong, and the neighboring processor reads from the buffer that was previously written and keeps on going. Note, this is where all these semaphores come in that are allocated whether the buffer is available and the buffer is ready. And you can build a stream like the one shown at top as a Dataflow. You can also do variants of broadcast or variants of this style of Dataflow. And the part that is very important, and I can do others where I do non-neighbor communication, where the black arrow on the right there is mapped over the interconnect network between the cores that I have shown you. What is very important, and you can do, for instance, also broadcast, where one core produces results that are used by all the other cores. The essential part is that you as a programmer don't have to worry about this. The essential part is that our multi-core compiler does all the work for you, including where the kernel's mapped onto which processor core, where are the buffers allocated, do I need a double buffer or not, do I need to allocate this and reserve the locks for it, and so we generate the main program running on a core, all the settings for the interconnect switches, and all the buffers. So you write kernels like a filter or an FFT or so on that works input buffer to output buffer, and we will do the mapping of those kernels to processors, the multi-core routing of those buffers between the cores, and all the other constraints. And last but not least, at the hardware end, you can conveniently also go to the FPGA fabric. And there's essentially asynchronous clock domain crossing and DMAs in our hardware interface there. And that's partly because your FPGA programmable logic fabric will not run at the same frequency as these cores that are running at a gigahertz and over. And you might have a conventional design that runs at 400 or 500 megahertz in your FPGA fabric, and you want asynchronous interfaces. Lo and behold, we really understand how to build those, and we have both the connection to the programmable logic and the connection to the network on chip sitting there, and so you can get in and out of your processor with these buffers seamlessly, whether it is mapped into another processor or in programmable logic, or you're trying to get to external memory. And you can get these streams routed. You can also use the processor subsystem to get both what we call real-time parameters or runtime parameters, have the ARM processor set filter coefficients or other things that are relatively infrequent compared to the hundreds of megasamples per second that you can do inside this array of processor cores. You can also go to external memory. This is an explicit choice. We have built, by choice, a machinery that is really good at high-speed signal processing and deterministic latency. That is very different than, say, a conventional CPU world where I have cache coherency and where I hope that from a coherency point of view the cores can cooperate, as well as I hope from a core point of view that there is locality in data and locality in time, which is why the caches work to begin with. If you now go to high-speed signal processing, that's not necessarily true. I have much more a streaming compute model, and I rapidly want to get a bunch of samples in, do some compute, push them out, and the next bunch of samples in and push them out. So we have chosen to build this local distributed memory processor cores with no cache coherency, with no caches, no instruction cache, and no data cache. What comes with that is the obligation to build a programming environment so that you can conveniently program this. And the challenge in the world has been, people have tried this before and made it very low-level programming available to end customers, and that wasn't that successful. So, key of the question is the programming environment. What you also get, of course, is the name of the game, that I can keep on doing my compute while my buffers are being reloaded and provided. We have programmed machine learning convolutions, FFTs, and wireless processing, digital predistorted. And what is very important is to understand that the name of the game, once I put all this hardware down, is how much can I reach of the peak compute. Now, if you're familiar with GPUs, they have a very different model. They have a model that I have threads, a thread needs memory, and if the thread misses the memory in the local cache, I have another thread that previously missed, but now has fetched the data and can keep on running. That's a model that requires two things. One, a very large number of threads to get close to peak performance, and two, a lot of local memory and external memory bandwidth to keep all these threads fed. We have explicitly chosen not to do that. We have chosen to build something with deterministic buffers, lots of interconnect, local memory, and we see programmed all the way to final applications that our kernels get in the 95, 80, and 98% for the applications that we've looked at. Now let's talk about the software for this. So we have several layers of software that basically cater to different audiences. If you really want to, the conventional FPGA programmable logic is the conventional FPGA Vivado design suite. You can build anything with conventional Verilog and VHDL as you used to. And you might have legacy code, and that runs there unaltered and a little bit faster because we're moving to 7 nanometer. We have built a new environment for the software developers, and if you're somewhat familiar with our software development kit for the Zinc and the MPSoC environments, you see the look and feel that you get there. But now we have added these AI engines that are these multi-core processors for which we've built a complete programming environment. And so what you see here is for each of them, we have its own environment. For ARM, you have conventional ARM compilers. For FPGA Fabric, you have high-level synthesis for C and C++ functionality into programmable logic and your conventional programmable logic. And for these AI engines, you have this graph of compute kernels, and the kernels are expressed in C and C++. And that all integrated in a full software environment that is up and running. What you can do with our AI engines is you get both for the single and the multi-cores, your run-of-the-mill integrated development environment, your compiler, your debugger, your Gantt chart performance analysis, your statistics of both your kernels and your multi-cores. once you take a good look at see is that this SIMD style processors can be very powerful, and for these application domains it makes an enormous sense to build libraries. You get some libraries from Xilinx, but you can also build your own libraries, and we see that in early customers there's emerging sort of a library team that builds the world's best FFT for the radix that I now want. And then there's users of these libraries. They say, let me stitch a graph together of these things that is beamforming or something like that. What we also see is this only makes sense if I have a good way of understanding what's going on in this relatively complex machine. And so we have error management, memory management, boot configuration. We have also in the new ACAP much more thermal management and power management. And I don't want to dwell on the hardware here, but there's both lots of counters in there. There's particular modes to set pieces that you don't use to sleep, or set pieces to sleep, nap, doze mode for whatever favor you want. Let's go a little bit on this Dataflow idea. You describe your Dataflow graph in C++, and it is really, think of it as a kernel that is just a function with an input buffer and an output buffer as I've shown you, and think of it as I have a bunch of these function calls one after the other. I connect them up. I can also have functions that sit in programmable logic in the end, but at the programming level you don't see that even. And we have then the multi-core compiler. The single cores like the functions A, B, and C are compiled to a single core, and then the multi-core compiler takes all the data dependencies that are these buffers I talked about and assigns the settings of the interconnect switches so that this routes this. Keep in mind this is word-oriented interconnect, not bit-oriented interconnect, of course. What you see also in the machine learning applications is that we have, we talked about this a little bit just before it in the lunch, we have an environment in which you can build your conceptual SoC on top of the existing FPGA fabric, and our recently acquired company like DeFi is a good example of that. DeFi is doing that to a large extent for lots of embedded, and our Xilinx XDNN is the compiler environment and corresponding template architecture in an FPGA that then gets you back to conventional compile times as if it were a highly tuned SoC built for this application domain. The same is going to happen for our next generation ACAP-based devices, and you will see Xilinx going further and further in the direction of Alveo-style cards that come with fully integrated environment, the right power consumption, and the whole software stack on top of that running, and you will see that emerging in the 7nm devices also next. We talked about this. The AI engines in the convolutional sense are really, really good at convolutions, ReLU, all the popular functions that you want to do there, max pooling, various activation functions. And you can use your AI engines plus the memory in the programmable logic to build your custom memory hierarchy. And this is basically by sizing the buffers at your C++ graph at the right level. The second piece is we also provide you a complete, quote-unquote, ready-to-go machine that is now at the framework level that can run your machine learning from TensorFlow compiled to this conceptual virtual processor. And then you combine that with video, genomics, database processing, and networking that you like. And here you see a little bit how we do this. We map the convolutions and the fully connected layers and the ReLUs on the AI engines, these vector processors that are really good at that. We have some buffer sitting in the ultra RAMs of the conventional programmable logic, and that way that engine can do the typical matrix multiply of activation times wait and really keep it all streaming. So keep in mind, the real challenge in machine learning is not matrix multiply. We all understand that. The real challenge is how can I stay close to peak performance given the problem at hand. And you see that in many literature in the machine learning domain, that your naive implementation is way off from peak performance that your official hardware could potentially achieve, but to get the data there is the real problem. What we see also here is we are convinced that what is going on, because of the inherent benefit of streaming compute done right and the tuning of the processors and the interconnect, we have a very different conceptual model than a multi-threaded GPU that sweeps in and out to external memory. And that power benefit you see already in existing FPGA implementations, and you will expand that power benefit with our highly tuned processor cores. And so we see that already, that based on our estimates, our VC1902 device, so that is a device with 400 of these math engine cores or processor adaptive intelligent cores, and it will do in the range of 75 watt on the card, and it'll run in a latency that is very competitive. Let's switch to wireless. I see basically 5G wireless is a whole bunch of new challenges. I want to pick one out of it. One of them is essentially the beamforming style applications that you see emerging. And beamforming has, if you take a look at it in much more detail, an enormous compute requirement. This is wireless at the infrastructure end, so you will have your own cell phone or IoT or driving car or so on, and all of them want connectivity to your base station or whatever infrastructure. And we see the characteristics of the compute there increasing rapidly, and we've tuned this processor to do this application domain very efficiently. What you see also there is the integration of A to D and D to A that we already started in our existing product called RFSoC will further be extended to A to D and D to A plus these kinds of processors. And then you can build your digital front end that way. You can build your protocol engine like a CPRI engine in the programmable logic, and you have a complete solution to that. What you also see is in the range of 1 million logic cells, but you can actually start processing very wideband, multiple antenna wireless applications. I don't want to delve into too much of the wireless application right now here, but we have clearly thought about this hard from the ground up on how can I do this. Let me come to a conclusion with one slide that is no glitzy marketing, but is just text. So I promised to talk a little bit, how do you get from an initial idea in research to changing the whole company, getting this as the lead difference in their platform, right? So keep in mind, many years ago, myself and a few others in the team were thinking, we're going to convince the company that a large array of processors is a good idea. This is a conventional FPGA company who thought that the switch from PowerPC to ARM cores is already quite a transition, okay? So you go and you do your initial investigation. Very rapidly, you need to quantify it. You need to understand what the challenges are. You need to understand what is potentially possible. And the big difference here is that we, in a very small team, built applications, prototype multi-core software tools, novel architecture, and initial estimates and even prototype on silicon, so that we have bounded the box of what we can do. And then in hindsight, actually, processor design, if that's your bread and butter, isn't that difficult. The really hard innovative part is the multi-core programming environment around this and making it so that it is sufficiently usable. What is also very important is architecture is full of choices. We have 32 kilobyte memory, why not 64? We have 512-bit SIMD vector lanes, why not wider, why not narrower? We are still trying to do and video and machine learning and wireless applications. What is a good common denominator for that? The part that we have really exploited, which is unique for this part of Xilinx, is we don't have to do everything. We don't have to do bit-oriented logic. We don't have to do AND and OR functions in the vector pipe. We don't have to be able to run SHA security on the vector pipe, because you have FPGA fabric next door that is actually very good at that. And then last but not least, you need to spend quite some energy to your colleagues who are in the product division, who also have all kinds of good ideas, who didn't have this idea, to convince them that your idea is potentially better than the idea they're working on, in the end, their call. So it's not only this. And the second piece, I'm very pleased to say, is the cooperation is, of course, one of teams. And so team building is essential. And what is also going on is the majority of my team is now the product organization. So I lost all my good guys and I go back to basics, square one, next topic. So successful research is doing good stuff, get the numbers right, understand the whole application, including the software, and work with teams across the board on multiple continents, in multiple locations to make this successful. If you do that, you can convince a company to build a whole new programmable platform. So with that, I want to conclude. I've talked to you about it, signal processing and AI inference. I've talked to you about it, that this is a software programmable with emphasis on deterministic and efficiency. And you can find all the references on xilinx.com under the /Versal. Thank you very much.